Ocean waves are a powerful force of nature, and understanding them is crucial for many applications. Whether you're designing offshore wind farms, managing port operations, or addressing coastal safety and coastal erosion, accurate wave measurements are almost indispensable. For marine construction projects, knowing the wave conditions determines safe working windows and determines structural design requirements. For coastal management, wave measurements help us predict erosion and protect the coastline. That is why accurate wave monitoring is essential. But how can we achieve it?
Now, here's something important to understand about ocean waves. Every single wave is different. If you stand on a beach and watch the surf, you'll never see two identical waves. They vary in height, in length, in time between crests. There's endless variation. So how do we make sense of this chaos? The answer is statistics.
To properly characterize a wave field, we can't just measure a single wave and call it a day. We need to observe the ocean over a certain period of time, typically 15 to 30 minutes, and that gives us what we call a wave record. From that wave record, we can extract all kinds of statistics that tell us what's really happening out there.
The most fundamental piece of wave data we collect is the surface elevation time series. Imagine a graph where time runs along the bottom, and the vertical axis shows how high or low the water surface is at each moment. This time series captures every rise and fall of the ocean surface during our measurement period.
But there's something fascinating happening beneath the surface. That seemingly up and down motion of the water surface, it's actually composed of many different wave trains, all superimposed on top of each other.
Each wave train has its own period, the time it takes between two consecutive wave crests, and its own direction of travel. Some waves might have a period of 5 seconds, others 10 or 15 seconds. Some are traveling northeast, others northwest.
This is where the wave spectrum comes in. Think of it as a way to decompose that complex surface elevation time series into its constituent parts.
The simplest form is the one-dimensional or non-directional wave spectrum. This shows us how wave energy is distributed across different wave periods. You might see a peak in the spectrum at, say, 8 seconds, and that tells you there's a lot of wave energy concentrated around that period. But waves don't just have periods, they also have directions. That's where the two-dimensional or directional wave spectrum comes in. This gives us the complete picture, how wave energy is distributed across both period and direction simultaneously. It's a more sophisticated view that tells us not just when the waves are coming, but from which direction as well.
From these spectra, we can derive what we call bulk wave parameters, single numbers that characterize the overall sea state. The most important one is significant wave height, which is calculated as the average height of the highest 1/3 of waves in the wave record. It's the parameter mariners and engineers care about most.
Then there's peak wave period, which is the period where we see the maximum energy in the spectrum, essentially the dominant wave period in the sea state. And if you have directional information, you can also determine the peak wave direction, telling you which direction those dominant waves are coming from.
So now that we understand what we are trying to measure, let's talk about how we can actually measure it. There are several proven techniques, each with its own advantages depending on the situation. First, let's talk about wave buoys, perhaps the most widely recognized tool to measure the waves.
Picture a reasonably sized buoy floating on the ocean surface. It's kept in position by a mooring line connected to an anchor on the seabed, but it's free to move with the waves. Inside the buoy, you'll find motion sensors measuring the movements of the buoy in multiple directions, up and down, but also forwards and backwards, and side to side. As the buoy rides each passing wave, these sensors capture its movement, giving us displacement time series that we can process into all those wave statistics we discussed.
The beauty of wave buoys is their flexibility. You don't need any fixed structures. No jetties, no piers, no platforms. You can deploy them virtually anywhere in the ocean as long as it's not too deep to anchor it. Therefore, wave buoys are very suited for wave measurements at open sea, away from existing structures. Now, let's move to pressure sensors. These are placed below the water surface and they rely on a completely different measurement principle.
As waves pass overhead, the water pressure at the sensor location changes. When a wave crest passes above, the pressure increases. When a trough passes, the pressure drops. By measuring these pressure variations over time, we can infer what the surface elevation is doing up above. The relationship between pressure at depth and surface elevation time series is well understood from wave theory, so we can reconstruct the surface elevation time series from our pressure measurements accurately. There are some limitations with depth. The deeper you go, the more the wave pressure gets attenuated, especially for shorter period waves, but for many coastal engineering applications, pressure sensors to measure the waves work beautifully. One significant advantage is ease of installation. If you already have a fixed structure, a pier, a jetty, an offshore platform, mounting a pressure sensor is relatively straightforward. You're essentially attaching it to the structure below the waterline. However, there's an important limitation to be aware of. Pressure sensors give you surface elevation, but no directional information. You can measure significant wave height, peak wave period, but not peak wave direction. The pressure sensor is measuring pressure differences from the waves, not the actual horizontal motions. The third major technique uses radar technology. A radar sensor is mounted above the water surface on a platform, a bridge, or any elevated structure, and it points downward at the water. The sensor sends out radar pulses and measures how long they take to bounce back. Since we know the speed of the radar signal, we can calculate the distance to the water surface with remarkable precision. As waves pass beneath the sensor, the distance changes continuously, and by recording these distance measurements over time, we get a surface elevation time series, just like with the other methods. Radar sensors have some compelling advantages. Because they are mounted above the water surface with no submerged components, installation is typically easier than with pressure sensors. Also, they are less exposed to the harsh marine environment, so there's less biofouling and there's less chance of damage. They still require a fixed structure to be mounted on, but that's often available in ports, on coastal infrastructure, or on platforms. Like pressure sensors, standard radar sensors measure at a single point and therefore don't provide directional information. Some more advanced radar systems, like X-band marine radar, can capture directional wave information by scanning larger areas of the ocean surface, but these are more complex and expensive systems. These are not the only wave measurement techniques out there, but they are the most accessible ones. You may come across other monitoring techniques involving, for instance, submerged acoustic transducers using ultrasound signals to measure the distance to the sea surface or to measure wave-induced flow velocities. There are wave staffs, essentially rigid poles that measure the up and down sea surface elevation in a very direct fashion. And then there's a whole range of increasingly sophisticated remote monitoring techniques involving, for instance, satellites or aerial platforms that can measure the waves over vast areas of the ocean. But these three that we have treated here are definitely the most practical ones and the most common ones for continuous practical wave monitoring. Understanding ocean waves requires the right combination of science and technology. Whether you require the flexibility of a wave buoy, the simplicity of a pressure sensor, or the robustness of a radar system, the key is matching the right technology to your specific application. At Obscape, we offer a complete range of wave monitoring equipment, including wave measurement buoys, pressure-based wave gauges, and radar-based wave gauges. Our equipment is trusted by marine contractors, coastal engineers, port authorities, and research institutions around the world. Are you ready to discuss which solution is right for your project? Get in touch with our team today.